basic. And graft it onto these special type of phases of oxometalates. So we proposed that polyoxometalates or oxometalates are the ones which are in the crystalline domain. They are like the solid state of matter, like they are having the boundaries, as Professor Kari Risanen has been showing you. They were having crystalline state, so crystalline boundary, hard state. And then you have this other state which are soft, mobile and diffuse, like the boundaries which Pierre Desjean or Professor Pierre Desjean was talking about, where the diffuse mobile boundaries of the Middle Eastern states in Middle Ages. So we propose to call them as soft oxometalates, right? So that means they are like liquid. You can have a charged metal oxide as a liquid in a bottle. Okay, so I'll be talking about these soft oxometalates in the next 45 minutes to 1 hour, and then I would also request you to ask questions wherever you have doubts or confusions. Now, with this I start, and of course, this work is only possible because I have a fantastic lab here at ISER, and we have been doing this work for last 15 years or so. So we have been developing this area slowly in bits and pieces. And this is because we have a fantastic group of dedicated students in the lab. They work very hard and they are very bright, and young people like you who create these results. So I am thankful to them for this, and they are also behind this organization of this GIAN program as well. Now, having said that, let us get started. So, I give you an outline of all the lectures on GIAN, which GIAN program, which I will be doing. So, I will first be giving today class 1 on soft oxometalates. Then the class after this, that means that is also today, I'll talk about microbubble lithography and catalysis. I'll show you how you can make patterns and how you can do catalysis with these type of patterns, right? So, which is also quite interesting, and I'll show you that you can make plastic conductors, you can make catalytic chips, all on nanoscale and microscale. And then in the third class, I will talk about soft oxometalates in catalysis. So, I'll show you examples of catalysis and what are the catalysis that you can do with these type of systems. And finally, on the final day, I have for you an innovation and entrepreneurship workshop, because I felt that most of us are not taught in a conventional sense the basics of communication, that how you talk, how you present yourself, and how you can think out of the box, whether you are going to work for industry or whether you are going to work in academia. So, I'll talk about those things in a packed manner, and I'll ask you to do some assignments also on that day, and I think you will have fun. That's the final day, and we will have a workshop where we will ideate, and everything we will tell you, and I hope you will enjoy. So, the basic idea of this course, as me and Professor Kari Risanan has been thinking about, is not only to have the basic, but also have a little bit of applied high research, and then ending with a scope for you, for example, to ideate on projects which have applied directions as well, and you can perhaps think of not only academic projects, but also perhaps you can think of innovative projects as well. So, that's the scope of this present GIAN course which we have taught, and in between we will have others also giving you the lectures on different applied aspects of basic crystallography, which you will be learning from Professor Risan. So, let us get started. This is IISER Kolkata at a glance, and some of these beautiful pictures were taken by my students, so I am showing them. So, it's really beautiful campus, you enjoy the campus, and there is a lot of natural flora and fauna. So, be careful from the natural fauna, because just now when we were coming, we saw some very interesting animal. So, I would request you to have covered shoes and not to go too deep into the forests and things like that, but just walk on the main, and the nature here in the campus is beautiful enough to impress you, even when you are taking walks in the main roads without walking into the woods and inviting any unnecessary awakening from the faunas of this area. So, now this is IISER, and yeah, and we are now in this building somewhere. So, this on this side. Anyway, so about our academics, so I just tell you about our lab. So, our lab is an excellent lab, for example. So, we have so far published around 110 publications in good journals like NatCom, Angavante, Coordination Chemistry Review, Journal of Materials Chemistry A, and so on and so forth. And we have also few patents, and we have also co-authored few books. So, that is to convince you also that you are hearing from someone or from us who are also working at a very high level in research in this field. Now, let us get started. So, as I said you, for example, if you are interested, you can have a look at this review. So, this is a recent review with Nidhi Kumari in 2024, and this one. So, as I said you, so these soft oxometalates are the soft matter state of charged metal oxides. And why they are important? They are important because they can serve as a possible model to understand crystallization. And I will tell you how we can use this model to understand crystallization. And not only that, it's also possible to explore kinetic states. And once you can explore these kinetic states, so then you can explore the possibility of photoredox catalysis. So, you can do photoredox catalysis because there is a presence of thousands of photoactive metal oxo terminal bonds. So that means when you shine light on them, or if you can excite them with electricity, they go into the excited states. And of course, another thing I would like to point out is that with structure from crystallography, you have the periodicity, you have the periodic boundary. But what happens when you cross the periodic boundary? What happens, for example, like about the structure of these foamy seeds, or the milk that you drink in the morning, or the coffee that you had in the morning? Have you thought of, for example, like why when you leave the coffee, there is a coffee ring at the bottom of the cup? These are all the paradigms that you can understand from the point of view of these transitions of soft matter into crystalline domain. And I will show you with case by case examples that how this type of material addresses the structure beyond the translational paradigm, beyond the translational periodicity paradigm. So this is important system to understand different methods of crystallization, and we will show you different transitions. Now this has also been getting some traction from the practitioners or researchers in the field. And so for example, Professor Mark Antonio, so this is Professor Michael Pope, who is like the Pope of the field of polyoxometalates, and he wrote the Bible of polyoxometalates. And in that work, he highlighted in the Encyclopedia of Inorganic Chemistry, he highlighted, and his student highlighted our concept of SOM. So which was quite nice, and we liked it, of course, with Professor Tatiana Furcht, Mark Antonio, and so on. Now, what we are planning to do, what is it that we are looking at? So what is it that we would like to do, or we can do with these type of systems in the next coming 10-15 years? We would like to have a platform type of material where you can do integration as well as differentiation of material, and you can create active matter, meaning that mobile matter, meaning the moving matter. So it's not only that bacteria or viruses can move, we will show you that you can indeed make motion or create motion by using these type of materials which are like life, which are lifelike. Now if you have this kind of lifelike, and if you take a systems chemistry approach in materials design, then what you have essentially in the center of this whole structure, you have the energy, and then what you need to do is you have to partition the system. Once you partition the system, you have immobile frontiers, closed systems. And from your basic thermodynamics, you know that your laws of thermodynamics are applicable for closed systems, right? Because if you have open systems, then thermodynamics becomes complicated, and you have different types of thermodynamics. So you have to have a closed system. You have to create partitions, you have to create vessels. And then you have to have reaction within these partitions. Once you do reactions within these type of partitions, then what you do, you essentially come up with harvesting of energy. So you can really take energy out of the systems. That means you can harvest, for example, solar energy or wind energy, and then you can harvest energy and you can use them in daily life. And I will show you with examples how, using these type of systems, we are able to convert carbon dioxide into fuels like methanol, ethanol, and so on, acetic acid, and so on and so forth. And then you can use reaction also to create motion. You can harvest motion, right? So you can make them move and you can have motion in them. And you can also use assembly and disassembly to create motion. So this is essentially the paradigm. I will give you examples of all these type of cases. The idea is then smart people like you who would later come and enrich us will perhaps be able to one day to integrate these systems to come up with artificial life-like systems, right? So that's basically the idea. So the output will be integrable and differentiable active matter systems. Now I give you first example. For this is what we collaborated with Professor Benthang and Professor Francis Fairport from China and Ghent University, Belgium. So what we did, we combined this type of JUCZ12, it's a porous organic framework. So we use this porous organic framework, and then to it we added the SOMs, the soft oxometalates. What we were able to get, we were able to get this SOM JUCZ12 nanocarpet, right? So that means you get a combination of both these, and that is based on charged interaction, right? So you have a complementary charge, one is positive charged, one is negatively charged, then you get these type of systems. Then what we did as a fuel, we added methanol and acid a little bit so that we were able to reduce these SOMs into more reduced state. Now, if you know that you are reducing your system, you immediately then know that you are pumping charge in the system, right? Negative charge you are pumping in the system. This would then reduce the interaction between the porous organic framework and the SOMs, and thereby there will be disassembly, right? So they will be moving away from each other, and that is exactly what happens. So there is a disassembly, and the disassembled oxometalates are released from the micropores, and this as an output gives you autonomously moving nanocarpets. So that's the output. So that means you start with an input, you are able to program it, the programming is your structural units, and then based on the interaction between these structural units, you can create motion. And this is something which we observed in real life. We analyzed the particles, for example, using TrackPy, so that is a Python-based systems. And this work was done by Apabrita Mollik, who is now in Czech Republic doing her postdoc. And what was the motion you can see? So Apabrita could get this type of particle. This is in 0 second, then in 1 second it moves like this, and then in 9 seconds it moves really along this trajectory over there. So there is nothing except this chemical interaction between the positively charged and the negatively charged particles, and we are charging them up to get this motion. So now one of the ideas which my present lab mates, colleagues are trying to pursue is, can we do this together with catalysis? And I will show you perhaps in the third class where you can do water cleaning with these type of systems. So they are like, you put them, these particles, in water, in dirty water, which was done by Apabrita also earlier. So you put these particles in the dirty water and you clean up the system totally. So which is quite cool and which is quite of a nice application. So we always believe, for example, in the application of the work together with the high level of fundamental science. And I would also like to urge you to think along those lines. Now this is one system. Then I'll show you, for example, the next system, that is understanding crystallization of oxometalates starting from the SOMs. Now what you see in this case is as following. You have this charged metal oxides, right? Like for example, we started with the most simple MO7 type unit. It's a heptamolybdate. It's MO7 O24 6 minus. It's a very basic unit of molybdenum based oxometalate. Now what we wanted to do the following. It's very difficult to understand crystallization, and it's a challenging problem. So how crystals are formed? So in order to do that, you have two competing processes that are going on, right? So one is the physical process and the other one is the chemical process. Now in the physical process, it's perhaps relatively easier to understand, but if you have both the processes going on, then it becomes very difficult to understand. So we took MO7, we made sure that there is no chemical reactivity, right? So this was a work that was done by Preeti Thomas, who is a graduate student of our lab. So she finished her PhD. So she took these MO7 type systems, and then without any possibility of any chemical reaction, right? And then what she did is she increased the volume fraction, the concentration. Now, once you increase the concentration, once you started increasing the concentration, this clear solution of discrete ions started giving way to the colloidal soft oxometalates. How did we know that? It was known because when we started with the simple solution, when we shine light on them, there was no Tyndall effect. It was a clear solution. So, for example, if you take a laser pointer like this, and if you have a container with water, you shine laser, you will not see the path of the laser through water, right? There is nothing, so there is no scattering. So, when you take this molecular liquid kind of thing, so this MO7 units only the ions, molecular ions, then you do not see any scattering. But what she found, if she raises the concentration of these ions, then she was able to see scattering. That means they were forming colloidal units, right? So, this is what she observed. And then if she raised this concentration further, she was observing crystalline polyoxometalates. So, absolutely crystalline domain. So, that means she was experiencing the transition experimentally from soft oxometalates, from molecular liquids, molecular ions, to colloidal entities, to the soft oxometalates, to the crystalline polyoxometalates. So, then we joined hands with Professor Nirmalo Ghosh, who is a physicist, and we looked at the emerging structure in these type of systems, which you can do with attenuated light. So, I am not getting into that, but you have to believe me that we could see the emergence of crystalline periodicity in this system. And what we then observed is that we were indeed getting a system where there was no periodicity at all, right, the MO7 units. Then there was an emerging periodicity, that means there was some local periodicity which was showing some kind of emergence of order in the system. And then finally, there was a total order in the system because we could get crystals, we could get diffraction patterns, we could get crystals. So, this was a transition, and then we explained it also theoretically. And what we did, we took this kind of rods and then we put Baxter type potential. What is this Baxter type potential? Baxter type potential is that you have a rod, then around the rod you take a very thin potential window, very, very thin. It's infinitesimally thin potential window. And when two particles come close, that means within this potential window, they are locked. They come close together, they are locked, and then they form extended units. And like this, there is a domino effect happening when all these particles are coming close and they are like locking with each other, and then thereby they are forming the crystalline polyoxometalate from the soft oxometalate. So, this was our explanation, and the beauty was we could calculate from this Baxter model the osmotic potential, meaning you know osmosis, right? So, when you have an osmosis, you can have an osmotic potential. So, you can calculate that osmotic potential, and we had it similar as the one we could get from the dispersion studies experimentally. So, this was a very fine piece of work. Then my other student, for example, a little bit later, Shaunik Pal, who is now in Czech Republic as a Marie Curie fellow, he took up the problem, and we thought that now we give it a little bit of spin, a little bit of twist. So, what we do, we change the pH of the system slightly, right? We are not doing chemical reaction, but we change the pH. What is the beauty of changing pH? Because you are changing the hydrogen ion concentration. Now, once you change the hydrogen ion concentration, then what happens is you are setting in a metal oxo metal condensation. That you can understand, right? This is from your bachelor studies, you have perhaps studied it, right? So, you have MO, then H, you put another H plus ion, then you have MOH2 plus with the oxygen having the plus charge, right? Then you have the next MO terminal unit which will then come and it will form a MOM type unit with the expulsion of water molecules. So this is the type of condensation which you can set in, and that's what he did. And then he was able to show that using this type of systems, changing the pH, it's possible to form MO8 type units, and it also follows exactly the same pathway, meaning you have the molecular anions which are going with the change of pH into colloidal units, and then or colloidal SOMs, and then with higher pH it is going to the condensation and getting a crystalline domain. And we were also able to get the crystal structure which is shown here. So we could easily get this type of reactions, right? And then when we plotted this in a ternary phase diagram, what we saw that within this domain, so there are three parameters: water, temperature, and oxometalate concentration. So we saw that within the SOM domain there is a crystalline domain of POM. So that means you indeed have a situation where you have the liquid like anions, they're there, then they form this colloidal entity which is a little bit more dense, and within this colloidal entity you get again the crystalline polyoxometalates, right? And this shows, for instance, that you can have a change in phase by just increasing the volume fraction or by increasing the pH. Now we thought that is there an application? And in fact, I am telling you the story a little bit in a reversed way, because we observed this result before all the nice explanations I gave you in the last slide, right? So what was happening there was with Professor Owen Banerjee's lab. What we were doing, we were taking a SOM dispersion and then we were shining laser on them, but not with this normal laser pointer, but with optical tweezers. So we put optical tweezers and then we were able to heat up this SOM type units, and then we could see that there was a heating up of the bubble. And once you have the heating up of the bubble, then you have a convection. Now, why there is a convection? This is because you know that the surface tension is dependent on temperature, right? So you have a change in surface tension. So that means when you are shining laser in the sample chamber, between the top and the bottom, there is a temperature gradient. Now this temperature gradient leads to a surface tension gradient. So when we were having this optical tweezer leaving its spot, we were seeing this convection. This is the same type of convection which you see, for example, if you take a glass of wine and you swirl it, right? And then you will see the tears coming on the glass walls. This type of convection is known as Gibbs-Marangoni type of convection or Gibbs-Marangoni effect. So because of this type of Gibbs-Marangoni effect, there was a convection current, and because of this convection current, the cooler part were having the SOMs and the hotter part were convecting the SOMs onto the base. Now when you are moving away the laser tweezer, you are suddenly cooling that part, right? And that induces a phase transition, and that would lead to the deposition of the crystalline polyoxometalates on the glass slide. And I will show you in the next class a little bit more detail what are the applications you can do and how you can do fine reactions like polymerization and so on and so forth. So then we were able to show it with Raman spectroscopy that indeed you have a transition from the breathing mode of these vibrations, which are on the range or on the sides of these nanotubes, towards the more crystalline domain. And then what we did, we also did a study where we were able to convert benzaldehyde to benzoic acid on these trails. So we not only formed trail, but also we did catalysis with this, right? And benzaldehyde was oxidized into benzoic acid, and this showed a sigmoidal curve. Now, the sigmoidal curve, as you will know, represents that there is heterogeneity in the system. This is very typical for heterogeneous catalysis. So, we could do site-specific catalysis with light using these SOM type systems. And I will show you in the next lecture what are the other things that we can do. But this showed a very interesting phenomena. What is the interesting phenomena? The interesting phenomena is that they are light active. SOMs are active or responsive to light, right? And then we were happy that Professor Masaaki Haga from Chuo University, he is also a leading figure of inorganic chemistry, cited our work quite in detail. So he said, for example, Roy et al. Have demonstrated continuous depositions and a line patterning of polyoxometalate molecules using the translated bubble. So this also shows the power of collaboration, you see, because this work was possible because of our collaboration with Professor Owen Banerjee. Using the laser physics, we were able to uncover a fascinating aspect of these type of systems, which we are now pursuing in our lab. So one of the systems which we have now got is a ZIF67 type system, which is a MOF, on which Khokon Manna, he is working on this. So where we show you can have water oxidation in these type of systems. So now, having talked about it, having said the photocatalytic activity, what we then used with this was the nice idea that was executed by Shontu Das, who is now a government servant working in a very high position. And so he observed that if you would see the SOMs and if you would shine light onto the SOMs, then they go into the excited state, right? The SOMs go into the excited state. It is similar like what Professor Karadisanan showed earlier with the electrons being kicked out and they are moving into the excited state and there are creation of holes, right? So what are photons? So for example, when you have the photons, so they impinge your SOM, and then what happens is that the SOMs go into the excited state, but they cannot be in the excited state forever. So that means they have to come down to the ground state. Now when they come down to the ground state, they emit an exciton, right? And you know, exciton is a combination of hole and electrons, right? So you have this hole and electrons combined. So what does the hole do? So the holes, they oxidized water into oxygen, right? And that's what is shown here. So water was split into oxygen by the holes, and then the reducing equivalent, because you know, if you break water, if you write the equation, you will get this type of equation for water oxidation, right? So that is 2H2O. If you write it, the equation, you have O2 plus 4H plus 4 electrons. So you have these protons and electrons together with the electrons. These are the reducing equivalents which were then injected into carbon dioxide, and Shontu was able to do that together with Shubho, who is now working in a company in Germany. So they were able to show this, and we were one of the early ones to convert carbon dioxide into formic acid together with oxidation of water. So this was a coupled process. It's like photosynthesis, so that's why these type of processes are known as artificial photosynthesis, right? So where you do photosynthesis, but then you don't have leaves, you have these SOMs, you have these entities which are then doing the magic for you, right? And at that time when we published, it was one of the highest turnover number systems with almost 1.4 million turnover number. And this is comparable to another system which was reported by around similar time by Professor Omar Yaghi and Chris Chang with cobalt porphyrin based systems, and they published it in Science, so which showed a turnover number of around 0.29 million. So that's the level which we could reach. But then we realized that we cannot go, or we cannot push so much with these systems. Why? Because these are OXO systems. Now with the word OXO, you know that they're intrinsically oxidizing, right? So when we wanted to have more reduced systems, we were not successful. We could not get more reducing system or more reduced systems. So then Shaunik Pal, so he's another PhD student of my group. Now he's working in Czech Republic. So he, when we joined hands with Professor Wolfgang Schöfberger from Austria, so he was able to show that you can change these ligand systems into corol type systems with a cobalt and a triphenyl phosphine. You are able to reduce carbon dioxide into ethanol. And when we did that, it was having also one of the highest turnover numbers, and it was also having one of the highest Faradaic efficiency. So we had, of course, a collection of different reduced products, but ethanol was obtained at a Faradaic efficiency of 47%. So which was really, really high. So what happens here is, for example, you have the carbon dioxide, then you have the reduced system, then you have the carbon dioxide anion, they will combine together to form glyoxal, right? CHO, CHO. And then you have a disproportionation via which you create ethanol, and that's how you can get the reduced product. Now, having said that, it's also possible for these type of systems to get these type of reduced products, and we then thought that what happens if we change this cobalt and we can change this to cobalt into manganese, then what happens? Then we were able to get carbon dioxide a little bit less reduced, but to more oxidized product like acetic acid, right? Because it's more oxidizing, so we could get into acetic acid. And later on, very recently, I will show you then what, with these type of systems, we thought of changing the systems, and we went on to a different kind of systems with the sulfur containing systems, MOS2 type systems, and we were able to have this sulfur vacancy, and then with this sulfur vacancy you can create electron containing pockets. Now, instead of working with the oxo, we now move to another chalcogenide, which is the sulfur containing chalcogenide, and then we were able to create the sulfur vacancy, and with this we were able to induce phase conversion of MOS2. Now, this was a work done by Kaushik Dash, who is now in Germany doing his postdoc. So what did we see? So Kaushik showed that you can have this type of sulfur vacancies, which are shown in VS, and you have the two types of phases, so in MOS2, so the 2H phase and the 1T phase, and it was based on the residence time of carbon dioxide into these phases, which would then convert carbon dioxide either into more reduced methanol or into less reduced formic acid. So this is what happens. Then I show you. So you have initially you have a system which is mixed with 2H phase and 1T phase. Then you have a phase conversion. This is done by sonication. You have the sulfur removal. So you have the sulfur vacancies. In these vacant sites, because you have high electron densities, so the carbon dioxide comes in and locks there, right? So the carbon dioxide comes and sits there in this manner. And then with blue LED, we are able to convert carbon dioxide in these holes either to formic acid or to methanol. And what you can see that basically the difference between the 1T and the 2H phase, how we can see it from the transmission electron microscopy. But what is important is that initially you have a condition where you get formic acid, but with time this formic acid starts getting converted into methanol and the formic acid concentration goes down. This is under open condition, and under closed condition you have always the formic acid, which is the dominant product. So if you have this, so this means that initially you have the formation of the formic acid, but when you expose them more to carbon dioxide, then they go to more reduced species, and that is how methanol is being formed. And we investigated it also with in situ IR spectroscopy, and we were able to show that how the emergence of the bonds take place, and that is how we came up with the explanation of the mechanistic pathway for these type of reactions, which was going via the methoxy unit and then forming methanol, or it was going via the formyl unit and becoming formic acid. And this was a work also where the theoretical works were done by our colleague in IISER Pune, Professor Prosenjit Ghosh. Now, what is interesting is that you have these type of systems, but we thought that means we are moving from oxo, from chalcogenide to the pnictide. So we thought we can change it from oxo chalcogenides. We have shown it with oxo, we have shown it with sulfur systems. Can we change it to nitrogen based systems and see what happens? And then it was Nidhi who took this challenge up, and this was a molecule which we got from Professor Shonjit Ganguly from St. Xavier's, and Nidhi took this challenge up, and then she was able to convert carbon dioxide into a series of products, including ethanol and acetone. So I'll show you what happens there. For example, you see now when you do electrocatalysis, how do you see or how do you know that you have any reactivity going on? This is a very simple question, right? So when you do electrocatalysis, so the first thing that you can do is you can run a linear sweep voltammetry curve, just a simple LSV curve, right? And then you run it in argon, that means where there you have no reactant, and then you run it in carbon dioxide, right, which is your reagent. So if your reagent is nitrogen, you run it with nitrogen. So you run it with carbon dioxide, and then immediately if you see there is a gap or there is a change in the potential, then you immediately know that some of the electrons are getting chewed up or taken up, right? So why is the electron being chewed up, or where are the electrons going? Then it was Nidhi who found out that these electrons are then going to reduce the carbon dioxide, right? So you are generating, essentially you have an electrode plate, you have an electrode, and then from the electrode you are charging the electrons onto your electrocatalyst. This electrocatalyst is then taking up the electrons and getting into a more active form. So you whatever you have, you essentially have a pre-catalyst that is going into the active catalyst, and this active catalyst is nothing but a diradical. That's what she showed, and we could see from the change in the distances. So this was like before electron reduction, it was like 1.26. After 2 electron reduction, it was 1.37. So that means there was an extension in the bond length, right? And then we had a twist in the amine groups, and where we had this carbon dioxide coming in and latching. So there were two types of sites. One was the end-on site and one was the side-on site. So where these type of combinations were happening. Now once these combinations were happening, then we were able to show, or Nidhi was able to show, that they go via acetyl unit, and these acetyl units would combine with methyl so as to form acetone type units together with acetic acid, and the Faradaic efficiency what we got in this case was 30.7%, which is quite positive and quite high in these type of systems, right? And this is the mechanistic pathway where you have the acetic acid pathway, where you see how the carbon dioxide, for example, comes on and sits on these type of azo groups, and then you have the creation of the acetic acid, and then you have expulsion of water together with the formation of the acetic acid in one pathway and acetone in the other pathway. This was a very detailed work which was done by Nidhi, and which shows that we have now come to the C3. right? So one was C1, which we have seen, formic acid. We changed the systems. Then we had C2, right, which was ethanol and acetic acid. Now we are in a position to come to C3, which is now C2 and C3, which is now acetone and acetic acid. So the next step which Nidhi and all others are working on is to get to butane or butanolic system, because you know butane is the cooking gas, right? So it will be fantastic if you can convert carbon dioxide into cooking gas, which will be really, really super cool and quite exciting to look at. So this was a paper which we published with Nidhi and Wolfgang and Shonjib, and if you have time, you can have a look at it. So with this, I think I have been able to show you that what we are trying to do or what we are aiming to do. We have in our mind a type of a quadrangular system or a quadrangle where at the center we work with energy, then we use partition, and then with this partitioning we do reaction, and then here we collaborate also with other labs, and here is the reaction phase where we can harvest energy. And I have shown you C1, C2, C3, and that's where we are, and hopefully we will be able to go to C4 and even higher systems. And then we are able to create motion, and then with assembly and disassembly we are also able to create motion. But the question is, can we develop systems which can do everything in a modular fashion but integrated together hierarchically or structurally, right? So that's the thing which we are interested in going. So what's next? So I have shown you SOMS as a platform for catalysis, lithography, and crystallization. And I'm not taking this introduction into time jail. So what's next is, in the next class, we will do microbubble lithography and we will talk about catalysis. So, and with this, we will go on to the third lesson on soft oxometalates in catalysis. So this again I re-emphasize, it's possible because of the bright students with whom we are able to work at IISER. So they work at a very high level, very dedicated, and really I was blessed with a set of excellent students and who are super charged to do things, to do their work, and also at a deeper level. So I would like to conclude with a note which I like very much. One of the scientists whom I have a lot of respect and who is inspiring us, not only me but all of us, is Louis Pasteur, right? So I am very, very much of a follower of Louis Pasteur. And you know, Pasteur was someone who was interested not only in basic sciences but also its application. But he worked at a very high level. And it was Pasteur's interest in wine that would lead to the ideation that germs are in fact responsible for transmission of disease. And he was the key person who in fact ideated this concept, which was later on taken over by Alexander Fleming and the invention of penicillin, and the rest you know is history. Not only that, Pasteur was also another person from the tartar crystals which you get in a wine vat. So when you make wine, you know you have these huge containers which are wine vats. You get the tartar crystals, and in these crystals he found handedness, which today is a huge industry of pharmaceuticals where you have the left-handed and the right-handed products and all this. So what I would like to inspire you is to, of course, do cutting-edge science, but do science with an eye on application. What is the need of your science in your society? And I'll consider this whole effort to be successful because we are combining a top scientist like Professor Kari Risanen, who will be teaching you basic sciences, but of course he's also doing science at a very high level with basic and as well as applied. And we will have also other scientists like us who would augment it with applications of crystallography, right? And then we will have this workshop where I would provide you with raw materials, and hopefully we will come up with some very cool projects which can have applied direction. So with this I conclude, and I am an editor of this journal, so if you have some things, please do send it over, and thank you very much, and I'll be able to answer your questions when you have. Thank you. Questions? Questions or comments, whatever? Yeah, you can take the mic. Yeah. What would be nice is if you also introduce yourself in one line. That's nice. Where are you from? What is your name?
So myself Shagota Chakraborty. I am from ICS Kolkata. And my question is that we are taking the porous organic materials firstly and adding SOMs on that, and then we are adding the fuels. So what changes does the changes in the structure generally occurs that the SOMs are becoming active. So why
Okay, okay,
it's
very
becoming?
nice. Yeah, thank you. So what we are doing, we are providing electrons into the system, right? So when you are reducing, you're providing electrons to the system. Now, when you are providing electrons to the system, the surface of the polyacid, which are SOMs, they become negatively charged. So the glue that is between the POF and the SOM, that gets corroded because that is proton based. So that proton is getting neutralized, right? So because of the electron. So you have an electron diffuse layer that is formed, and that would lead to the chopping off of these two units, so which frees the SOMs from the POF pockets, and then they start moving. That's a very good question. Is clear? Yeah, thank you. Very nice question. Any more question or comments? Okay, if there are no more questions, I think we take a short break for 7 minutes, and then we will go on to the next class. Thank you. So yeah, just take some rest, and then we will start again. Thank you. So welcome back. So now I will be talking about patterning, and I will talk about what we have been developing in our lab together in collaboration with Professor Owen Banerjee's lab, the microbubble lithography. So, and we will show that what are the applications of this microbubble lithography in catalysis. And as the name suggests, so you have seen it in the last class where we have shown that how you create the bubble, you translate the bubble, and then you make patterns, right? So when you have systems in place, it's also important that your systems get smart. They can write things, and writing is nothing but coding. So you put some information and then you transfer this information, and then that information will have some meaning, and when you are looking at it, the information gets across and you are able to decipher the information. So it will be nice if chemical systems can have this capacity so as to be able to code and decode, right? So, and we are able to write these type of materials on simple surfaces like glass surface, ITO electrode surface, and so on and so forth. And we are able to do catalysis with this. And what is the meaning of this microbubble lithography? So we create bubbles which are microscopic. So we create microbubbles. And then with these microbubbles, we are able to create patterns because there is this condensation, what I talked about in the last class, right? So you have a laser, I just repeat it again. So you have a laser trap or an optical tweezer trap, then you have convergent lasers, right? And then they heat up the local reaction environment in the sample chamber of this optical tweezer, and they create bubbles. And these bubbles, these micro bubbles, have a Gibbs-Marangoni type convection current around them, right? And these convection currents would be created because there is a surface tension gradient, because on one surface is more heated than the other surface in the sample chamber, and this will give rise to this convection current. And when you have this convection current, then when you move the laser bubble away, then they cannot get the time to move. They indeed then condense with each other and they crystallize and form patterns. And that's how we are able to write patterns, for example, like this, which looks quite neat and clean, right? So you can just write these patterns on surfaces as you want. And what we have seen, that people from schools, even younger ones than you, they have come and they have played with the joystick and they were able to make houses, gardens, whatever drawings they wanted to do with these joysticks. So it's that much of a control that you can exert with these type of systems. Now, what we want with this type of writing is, our future question which we would like to ask is, can we enable catalyst systems to write their own catalytic codes? That's an ambitious challenge, but that's what we would like to do maybe someday. So that's the overarching view of this. So now here writing is coding, and we would like to partition or to create the codes by means of creating partitions in there. And we would like the catalyst systems to be able to write their own partition, their own codes in there. So this is how it looks like. So for example, you have this type of microbubble. Now around this microbubble, you have the convective flow, right? So you have just the convective flow moving around the microbubble, and you have here at one point you have the heated area, and here you have the cold or cooler area. And because of this difference in this hot and cold region, you have the convective flow. And I want to remind you that these are all experimental results. So these are not theoretical results or whatever. These are all hard experiments, and these are all experimental results which I am showing you. Now you are able to have this convection current, and then you are able to form this type of conducting pattern. And if you are interested, I would invite you to read this review with Owen Banerjee and myself in Nanoletters, which is published a couple of years before, where we archive this whole study which we are going to present, or which I am going to present. So what happens here is the following. So you have a system where you have the light source and you have the sample chamber. In this sample chamber you have the SOM dispersion, and this is very, very general. Now we have shown that it not only works with SOMs, it works with any kind of materials, but of course with SOMs it's a little bit easier because they are more tunable and they have a diverse range of properties. That's where it's a unique system which is applicable in these cases. Now, this work first was discovered by this guy Basudeb Roy, who is now a professor or an assistant professor at IIT Madras. So what Basudeb found when we were doing these type of works is that we were trying to trap SOMs. That's all we were trying. We are not trying anything else. So in optical tweezer, we have these two Gaussian beams, and within which we wanted to have the SOMs trapped. Just tweezer is like this, right? So you hold it. So we wanted to hold the SOM in there. And what we found, what Basudev found, is that whenever he's trying to do a pattern of, whenever he's trying to trap the SOMs with these optical tweezers, there was a jet of an ink-like thing that was coming off in course of this patterning. So this was an optical kind of a thing, and he was really persistent, and he then did a lot of control experiments. We did a lot of control experiments to understand what is happening, and then we were able to see that what is happening is the following. So I will show you again. So you have here the sample chamber and the cover slip. So in between the sample chamber and in between the slide and the cover slip, you have the sample chamber, and here you have the bubble. Now this is the micro bubble. When you are shining laser, we see the bubble, this tiny bubble grows. It grows in size, right? Because it gets heated up. Now when it gets heated up, it's not isolated. It has all the SOMs around it, right? So because it has all the SOMs around it, so then what happens is that when you have this heated bubble, you see a current of SOMs around the bubble. This is because of this, as I mentioned earlier, the surface tension gradient. Now when you have this surface tension gradient, the SOM bubbles, the SOM units, they come from the heated part to the cooler part, right? And then if you move the trap, the laser trap, if you move the laser away, then there are two possibilities for these SOMs, right? One is to move with the bubble, just to move with it, or the second possibility is not to move with the bubble, which is less likely. At least that's what we thought intuitively. They will perhaps stay back. And that's why in science, as Professor Kari Risanen already mentioned in the first class, that you should believe, or you should go by the data and with your brain, not by the tendency which you are going to have when you think a little bit, because you have to be careful with your thoughts, and you always have to base your thoughts on data, hard data. So what we saw is that this type of phenomena, this type of transition or phase transition is happening, and that is why Basudev was seeing this jet black ink-like thing that was forming as he was translating the bubble, right, which was not expected. So if you don't translate, if the bubble was moving, then there should not have been any translation, right? So there should have been no translation, nothing, but you will have the particle moving with the optical trap. That is what was the original idea. But then this was what we saw, and then with this transition we were able to write, or Basudev was able to write patterns, and with this we wrote patterns like IISER. You can read it. So that is what we wrote, the name of our institution. And now, as I said, we can write any kind of pattern, whatever we want to write. Now, and we were also able to put some other units like fluorescent molecules in there. We put carbon nanotubes in there. We were able to pattern all these together with the SOMs. And then we thought that can we use them for some concrete application, because that will be quite interesting, because then you can miniaturize catalysis, right? Because it's always, there is a demand that if you can do miniaturization and if you can do reactions on confined surfaces or on small length scales, because that gives you an advantage or a new opportunity to do multiple turnovers, right? So that means you can reduce the size, and that's essentially one of the guiding principles of nanocatalysis, which you are familiar. So this is of course not nano, because with light, again, Kari showed in the morning the electromagnetic spectrum, entire electromagnetic spectrum, and you know that with light here we cannot go to nano. We can stay up to few hundred nanometers. Why? Because visible light has that limit. So you go to the limit of visible light with which you can do these type of patterns. So you can have patterns with width of few hundred nanometers. And not only that, what Vasudev also showed, you can see different widths of these type of patterns, right? So this is more thin, this is thicker, this is even thicker. That happens with the speed of translation of your laser tweezer. So if you translate them very fast, then the bubbles do not have time to grow that much in size. You pull them very fast, you get thin patterns like this one. But if the residence time of the bubble with the laser, the contact time or the residence time, whatever you call it, if it is higher, then they have more time for residence. Then you get thicker lines or thicker trails. And if you reduce the time even more, you have really big dark trails, which you can even see with naked eyes. So that's kind of the power of this. So you can control the thickness or the width of these type of bubbles. And this I have shown you. So then what, with Vasudev, we also joined hands with Benthang and Professor Choshilan from Jilin University. So they made this type of porous organic frameworks for us. And then we were able to put these MO7 type units. This is positively charged, this is negatively charged, this is a very simple unit. You have seen this unit again earlier, right? So we try to work with MO7 type units because this is the most simple polyoxometalate for us. We don't want complex polyoxometalates because then the interactions become difficult to understand and it becomes difficult to go over there. So then we were able to see that when we are loading these SOMs on the POFs or porous organic frameworks, there is a domain where you have unstable dispersions, right? Unstable dispersions are like this. So I'll tell you a little bit about the dispersion so that you know it. So for example, if you take stones, right, and if you put them in water, if you take sand gravels, you put them in water, they immediately settle in the water, right? But if you take, for example, sand grains, grains of sand, you put them in water, they will not sink that easily, right? If you shake them, it becomes a little bit turbid kind of a thing. But if you take silica, silica nanoparticles, SiO2 nanoparticles, and this is a famous method which is known as Stoiber's method of synthesis, which is with silica, so which is with TEOS, tetraethyl siloxane, and then you get a clear turbid solution. You get a turbid solution. There is no question of settling down whatsoever, right? That's because you have then charges on these particles which repel each other. And this repulsion is stronger than the gravitational field that is acting on them, on the stone, for example, which would lead to its settling. You understand, right? So this repulsion would give them the stabilization. So essentially you have charge stabilization in these systems. But when you do not have charge stabilization, when you do not have this type of repulsion, then you have unstable dispersion. That's what it is called. So that means it will settle down. So if you do the experiment, and you will see when you have this SOM and POF, they will settle down, and but after a certain loading, you see that they form stable dispersion. So you see when the ratio is 20-fold, 30-fold, and so on and so forth, they're stable. But with less, around 10-fold, they're not stable. So that means they are just forming unstable dispersions, right? And then we looked at the IR spectroscopy, and here is another important point. We could not get the crystal structures here. Why? Because we are in dispersion. So we are totally working in dispersion. There is no translational periodicity, so we cannot have crystals. So we are having liquids, and for liquids, of course, you can get structure, but that is by static light scattering. In this case, we didn't do static light scattering, which is exactly same principle as the one Curry will show you. It has the structure factor, it has the form factor, is exactly the same. Only difference is that you have to assume in static light scattering the form factor to be that of a sphere and then solve it. When you do dynamic light scattering, you also again do the same thing, but in that case you have to find the diffusion coefficient, and this diffusion coefficient finding also has to have an approximation about the shape of the particle. So now, having said that, then that's why we looked at the IR spectroscopy, and we were able to convince others and of course ourselves too that you have a combination of this SOM and POF. And then we used this lithography, and we were able to write patterns like this. Now, and you can see these patterns. So these are really high on the surface, and then as you translate the laser, like the way I am doing, literally you do it on the microscope stage and you get this type of patterns. Literally you do this and then you will get it. And then when we do a line scan of on these particles, what we observe are these elemental compositions. So you know that on these particles you exactly have these units together, right? So that's what the power of this technique is. And when we do this, we also see that when you do a cross-sectional line scan, I have not shown it, but it's like this, then you see at one point there is nothing, then suddenly it goes up and then it comes down. This is the molybdenum, the yellow one is the molybdenum, the green one is the oxygen, and the red one is the carbon, and the violet one, you cannot see it here, but I can see it, but you cannot see it from there. That's the phosphorus. So you have all the material, all the elements that are present elementally, right? And we also did select area electron diffraction, which you have heard also in the second class from Kari, that you can do electron diffraction. So select area electron diffraction, and we were able to see that they were like liquids. So we do not have a crystalline lattice or something, we just have liquid-like structure. So now what we were able to do is that this MO7 based SOMs were likely to get into the crystalline domain, but only in a macroscopic scale. Now, what we did then, we looked at the Raman modes, and this is what we found, that there was a difference in the Raman stretches, and that's because you have weakening of the bonds. And we also did porosity measurement, and what we found interestingly is that the pores sizes were changing. These were the pores which were in the pristine compound, after doping with the MO7, these pores totally disappeared. So that means they are going and sitting on the pore and creating a surface area which is accessible for your reactants. And the stability, we also checked it with TGA. And then what we found is, when we do the reaction, we did the reaction, and this is a work, as I mentioned you, this was done by Preeti Thomas. So when she did this reaction, she was able to show that with an external standard, there was a possibility that external standard was DMSO. So we added DMSO as an external standard, and using benzoic acid. So because we were studying benzaldehyde oxidation to benzoic acid, she was able to show that this peak, which was signature for the benzoic acid, it slowly increases, and it only increases on the trail. And if you go out of the trail, there is no reaction whatsoever. So that's why we called it site specific reactivity. And not only that, we were also able to see that this type of sigmoidal kind of behavior, which indicates that there is a heterogeneity in the system, and this is very typical for heterogeneous catalysis, because you have a cooperative phenomena that happens during the catalysis, and that's why you have this type of system. So this is a signature for any kind of heterogeneous catalysis. And we found that, that's what I was saying. So we did reaction, for example, over here, right? So when we did reaction over here, we were able to get this type of conversion with respect to benzoic acid and DMSO. But when we move away from this, so when we do reactions over here or over here, we got a flat line. So that means there is no conversion going on. So it's very site specific, and you really have to see that you are putting your product, your reactant, just on the trail or just on the surface of these materials. Then we thought, okay, it's fine. Can we take up some more challenging reactions? Can we do some little bit more challenging reactions? Now, what is a little bit more challenging reaction? We thought, can we do polymerization with these type of systems? Earlier, this was a work that was done by one of my earlier undergraduate student, Atharva Sahasrabuddhe, so who is now in MIT. So he did this reaction, and you took the polyoxometalate, he shined light onto this. So when you shine light onto this, then it goes to the charged state, excited state. Now when you have in this excited state, you have butyl methyl imidazolium. Now butyl methyl imidazolium has these hydrogen atoms over there, so that can be transferred. So it's like a hydrogen atom transfer. So when you have this transfer, then you create an imidazolium cation radical. So now once you have this imidazolium cation radical, you have this oxometalate is being reduced. Now if you take this oxometalate, put it in open air, then this oxygen would get reduced into water, and your oxometalate or polyoxometalase is regenerated. So that's how you create this closure loop. And here, this butyl methylimidazolium radical would then polymerize any kind of monomer, whether it's a vinylic bond or an allylic bond, it can polymerize these units, right? So this was done in conventional condition. And what we also found in this type of reactions is that you have these closed pockets, elliptical pockets of butyl methyl imidazolium, which has a diameter almost of around 1 nanometer and width of around 0.46 nanometer. Now, by the way, this is crystal structure, yeah. So this is exactly from the crystals, and this is from the diffractometer. So we get the crystal structure, and then we were able to see these type of pockets. So these type of hydrophobic pockets were responsible for holding the nascent oligomers which were being created, right? And it was then what we observed is that we changed the loading. So once we change the loading, what we find that the molecular weight increases. And this is very, very simple, because when you have a radical polymerization, you know that if you have lesser and lesser radical, because you are loading initiator, right? So you can change the initiator, right? So if your initiator loading is higher, so if you put more initiator, then this ratio is small, so this is over here. So you see the molecular weight is less if you add more initiator. And this is from your basic knowledge of polymer science, that if you add more initiator, then you have much more radicals. Now those radicals, because they are much, much more, the chain length that you can create with these type of radicals is much shorter, as compared to if you put less radical, and then you get much higher polymeric weight, molecular weight. And this is what we had observed earlier. So we thought, okay, now, yeah, so this shows that it's a free radical pathway, where, as I said, you decreasing the initiator increases the molecular weight. So this is one of the acid test for free radical pathway. So we thought, okay, can we do these type of reactions with different monomers? And we were able to do it with different monomers, and we put some radical quenching agents, and then we were able to see the same kind of effect. But as you can see, the scope is not bad. We have styrene, butyl methyl methacrylate, vinyl acetate, methyl methacrylate, and so on. So what we were able to see, for example, is that this reaction goes perfectly fine, and you have a very nice recovery. And this is almost 100% conversion, and you have a very nice recovery that goes on. And you see in the reaction in the lab how it looks like. So after the reaction, this looks a little bit dark. You now put it in open air, right? And then you reoxidize this oxometalate, and then it comes back into its colorless native state. So that's how it's a totally recoverable reagent, recoverable catalyst. And then the question that we asked is, can we do catalysis, this type of catalysis, under optical tweezers? That was the question, because we have done it under normal light, right? So this type of light, can we do this catalysis under optical tweezers? So then again, Shontu came up with this nice idea that yes, we can try. And so what we did is then combined MO7 with pyrrole. And then what happened was very, very complicated. We didn't expect it to be that complicated, but it was really quite a complex thing. So what we saw is that there is a creation of a pyrrole radical, which would then combine with another pyrrole unit, with the conversion of this reduced MO5 into further MO4, and then that would lead to a kind of a clicking, and then you have a full polymerization. And not only that, you have these MO4 units which are forming MO2 type units, and they are acting as a dopant, because this is electron rich, and they are acting as a dopant, and they are doping this and forming this very interesting polymer SOM composite. We didn't expect it when we started doing this reaction, that it will be so complicated. And this work again was done with Owen Banerjee, because we do works jointly on this type of themes, and it really took us very long to understand what's going on, because it was very, very complicated. And then what we found was following. So Shontu was able to form these patterns, and then you have this kind of topologies where you see sharp valleys on the pattern. So these are pattern pictures. On the pattern you see sharp valleys, and you can form a little bit more rounded structures. Now this gave us the first time hint that there might be some soft polymeric materials which is enabling us to form more rounded structures. because crystalline patterns would be sharp and straight. So this was a very important observation from Shontu, and then we deciphered this entire pathway with XPS and so on and so forth, the full story. And not only that, then what we found is when we change the SOM concentration, then we saw that there is a certain concentration of SOM at which there is a maximum conductivity. So we then measured conductivity, and by measuring conductivity we were able to see that we have in fact made plastic conductors. So plastic conductors, you know that polymeric things which are conducting, so those are the plastic conductors. So we have come across plastic conductors, and the conductance is also not that bad, it's around 600 Siemens per centimeter. Not only that, when we used it with pyrrole, we also got these type of conductivities, and we saw that beyond a certain concentration, the conductivity goes down. So that means you have a certain available area on the plastic polymers, which are the pristine polymers, where the SOMs can be accommodated. But beyond that, you cannot do that, because you are then disturbing the intrinsic conductivity of these type of polymeric units. So we were quite happy to see that what started out as a simple trial experiment for forming polymerization reaction, or for doing polymerization reactions with oxometalates under optical tweezer, resulted in three distinct phenomena. What are those three phenomena? Number one, you have the pattern formed, right? That's the simple phenomena. Number two, you have the reaction going on. So you have this reaction where you are creating MOO2 type systems. And number three, these MOO2 type systems are acting as a dopant, and then they are combining with the polypyrrole and thereby forming the plastic conductors. And we were able to show it with other monomers like aniline and so on and so forth. So this shows the possibility of sometimes emergence of synergy which are not that planned, because we didn't really plan that it will be a conducting polymer. We just wanted to do a polymerization reaction, and we ended up with a conducting polymer altogether. Next, okay, this is already published now. So next is nice work by Rakesh and Khokon, who is in the audience. So what Rakesh did with Khokon together, they wanted to do a pattern, but this again was a complicated molecule. It was tetrabutyl ammonium together with phosphovanadate and tungstate type unit. So where you see this tungsten 9 is substituted with PV3. Now these formulas seem very intimidating or complicated, but they are not. You can close your eyes and deduce these formulas. How? For instance, initially you have a PO4, that is phosphate, right? PO4. Now a PO4 is a tetrahedron, right? So now a tetrahedron has how many vertices? 4 vertices, right? So now each vertex, if they have a tungsten 3 cap, then this tungsten 3 cap means you will have how many caps? 4 caps at most, right? That means that will make it PO4 W12, right? Because each one is a W3 cap, so 4 caps will make it W12. And then oxygen will be how many? Because these are tungsten oxide is WO3, so then it is oxygen 36, right? So then PO4, 4 oxygen, 36 oxygen makes it 40 oxygen. So that's your 40 oxygen, right? And you not only have here tungsten, but also you have a vanadium cap. So instead of 3 tungsten, if you put 3 vanadium, then you have PV3W9O40. Okay, so that's a polyoxometalate, right? So we took this polyoxometalate, and uh, these are the molecules whose crystal structures can be determined from X-ray crystallography, and as you will learn from Kari. And also there is a lecture by Professor Shamor Dash who will talk on the polyoxometalates in application of crystallography in polyoxometalates. So now anyway, so what then they said that they took this, and then what was observed, when they have this pattern, they did everything like regular, right? So like the way they were doing this full patterning and so on. And then when they did the pattern, then they did aniline, and they were able to oxidize aniline into nitrobenzene, which is not trivial because this is a tough oxidation reaction, and they were able to do it under ambient condition. So I was very confused. I insisted that they repeat it. We did several control experiments, but every time they came back and said that that's what is happening. So then we came up with the idea that what is happening is, we were lucky in this case, right? So what we saw is that when you have a pattern, right? Now in this pattern, the molecule, the reactant molecule, what is the reactant molecule seeing? The reactant molecule is not seeing this vanadium, tungsten, whatever, or TBA. The reactant molecule is seeing an oxo surface because you have all the oxygens on the surface, right? So the reactant molecule is seeing an oxo surface. Now when this reactant is coming, it is forming a hydrogen bond with this oxo surface. That's all it is doing. So it's anchoring, right? And then when you are shining laser, then what is happening is there is a hole, an oxygen vacancy that is created on the surface. In the earlier class, you have seen sulfur vacancy for CO2 reduction, right? So here we are seeing, so what Khokon and Rakesh, they saw is that there is an oxygen vacancy on the surface. And because you have oxygen vacancy, what does it mean for the molecule? For the molecule, it means nothing, but it means some electron densities. And then it was possible for the molecule to just replace this nitro with a more reducing, sorry, amine, sorry, not nitro, amine, with a more oxidizing oxo unit, and then creation of the oxo surface with the concomitant oxidation of this unit. So you have these two parallel things that are going on and that are oxidizing as well as recreation of the surface, because surface cannot be with hole, right? Because hole means there's something vacant. And that's how this whole oxo surface on the SOMS was regenerated, and this cycle continued. So then they determined the oxo vacancy with the lattice oxygen and the oxygen vacancy with XPS, and we were happy to see whatever we were proposing falls into the place. So you see, there are 3 types of reactions which I have shown you so far. So the first one is with benzaldehyde going to benzoic acid. That is very, very simple reaction, goes on with relative ease, right? The first one, that was the one which Preeti did. The second one, which I showed you with Shontu, that was what we did not expect. That was the patterning together with the formation of a plastic conductor, right? We started with pyrrole, and then we were able to form polypyrrole, and then the dopant, the reducing agent actually became the dopant, and this formed this MOO2, and then this was the combination of MOO2 together with the polypyrrole and polyaniline and forming a conducting surface, and we showed you very high conductance. Now the third one is even more interesting, because here we were able to create oxygen vacancy, right? And with this oxygen vacancy creation, we were able to do a rather difficult reaction of aniline getting converted into nitro, right? So these were the things and we did the Raman spectroscopy before and after and all, and IR spectroscopy, and we were able to show that it's recovered. Now you see, these are some nice pictures to show you, and on the characterization. So this is how the trail looks like. It's a clean trail. And another thing is also important to keep in mind: our trails or patterns we write becomes more and more nice because we are getting more and more experience on how to write patterns, right? So that improves our skills of writing patterns. And yeah, and then we have this type of units, and this was the unit which was present, and then we were able to show that how this reaction is taking place, and we were able to show that we indeed have a composite and which is having this reaction going on. So this has been already published in Materials Advances. So if you are interested, you can have a look at this paper. So what I have tried to show you today with the second lecture is that how you can use microbubble lithography for your reactions, and I have shown you at least 3 different types of reactions. And there is another reaction which we have done, which is a paper under review now, where we have used a MOF-based system. This is a work of Kokon, where we have used MOF-based systems to do water oxidation. And this is something which we have done, and I hope that next time when I speak with you, I'll be able to tell you more stories. So with this, I stop now, and I'll be very happy to answer your questions. Thank you. Questions or comments or whatever, it's fine. Yeah, I heard something. Oh no. Yes, yes. You should take the mic and introduce yourself and then ask questions.
Hello, I am Dibbajyoti. I'm a second year BSMS student here at ISER Kolkata. Sir, my question might be a little silly. Actually I didn't know about the concept of plastic conductors. So, sir, as you mentioned, the conductance is around 600 Siemens per meter, which sounds very little as compared to extremely negligible as compared to the metallic conductance, which is at order of like 10 to the power 6 or 10 to the power 7. So, sir, what are the applications of such materials like plastic conductors?
Yeah, very nice. Thank you. So it's a nice question. So these are the conductors which are conducting, and if you have very small application, very tiny applications, for example in MEMS as actuators and so on, where you need to have tiny changes in the conductivity to so as to activate or actuate your systems, then these type of conductors can become useful. So for example, in small circuits which you would like to prepare, you don't need so massive high conductance, but you need low conductance so as to do this type of actuations. So that's where this can be useful.
So, oh, sir, another question. Actually, I interacted with Khokonda before on DCS day about that micro bubble lithography, but I forgot to ask him some questions. So, sir, does it like the micro bubble lithography, does it like improve any Faradic efficiency when we like use micro bubble lithography in actual electrolytic setup, like, and we do the reduction process? So does it affect in better, like, does it give better efficiency or something
Okay,
related to?
that's very nice question, very clever question.
No,
And
actually, I did interact with Khokonda, but
yeah,
I didn't interact in details, so
yeah, yeah,
that's all.
yeah, that's a very nice question. So what I can tell you, we do not know completely, but what I can tell you from our own thinking, from my own thinking, I'm thinking loud and I'm telling you what is happening. So Faradic efficiency is essentially how much of your turnover, how much of your conversions you are having per coulomb of the charge passed, right? So that's your Faradic efficiency, right? So now if you have a system which is becoming more efficient catalytically, which is being done in the microbubble lithography, right? So that means you have more active surface areas. So I think your Faradic efficiency will go up. I think, but I might be wrong.
was the actual confusion I had when I interacted with Khokonda. He used this term active surface area, or
Mm-hmm.
that is where I was getting confused. What does actually active surface area
Yeah,
mean?
so they're very good. So there are two types of things which are important to keep in mind in catalysis. So one is the pre-catalyst and the other one is the active catalyst. So what normally you add in your reaction or electrochemical reaction or any reaction is the pre-catalyst. That is not the active catalyst. So for example, in the work that I showed of Nidhi, where we showed this azo type systems, and I showed that this goes into the diradical, that is the active catalyst. So what we mean by that is that you are patterning something which is the pre-catalyst, but when it is undergoing a reaction, it is getting converted into the active catalyst. Now if you ask me what is the nature of the active catalyst, that's very difficult to tell, at least in the ZIF type system, which I anticipate, right? So that's a little bit difficult for me to tell now because we do not know it completely, right? So but that's the difference. And but theoretically speaking, I think understanding it, it will be like this: your active catalyst, whatever it is, it will be nanoscopic, and in the nanoscopic domain its efficiency will increase, and because it will increase, so the Faraday efficiency should increase. That's my take, but I am open to be proven wrong, and when they do the reaction and get the result, that's we should listen to the data. But very nice, thank you. Okay, any more questions or comments?
Any more? Any other curious mind here?
Okay, so if not, then we stop now. So we will resume on Monday, right, in Monday morning, and then see you on Monday morning. Huh? What was that? Okay, so thank you.